Okay, so today's date is the 16th of February 2020. It's like the time now is 11:02 p.m. So I'm gonna go to chatgpt.com, but I'm gonna give some transcripts. So I'm gonna give at Monday AI my transcript. Where are my transcripts? So our transcripts are on Chrome. Basically, my transcripts are basically updated to my YouTube channel. So once again, guys, they're here. The pink noise. I don't have my transcript here. Basically, I'm gonna get traffic from here. So basically, this one traffic. Yeah, for Monday AI. So once again, guys. So today we're gonna work on some kind of problem, but you just use my AI assistant to do it. Tell me to do it, but do it articles. So I'm already gonna. So basically, this is my article. Wait for a second. Open Monday AI now. This is official. So today we're going to be talking about tomographic computing, but about a bit from the hot world. But so I'll do something so. Control X this. Basically, I'm trying to talk about tomography to go to my AI system here. So I'm gonna chat for tomographic computing. Text. So I'm recording this. So let's check. Okay, so okay, tomorrow. So one part is generalization. Different to for 1 second. Somebody else here. Where is she? He. So usually let me just So basically, I got what I needed now, guys. So guys, let us use an AI system. So the quantum radio here. So no, let's show what I mean. So my AI system unnecessarily. Yeah. You want to listen to me? Listen to me. Are you hearing me, Monday? So listen to this properly. So basically, so this has to be done properly. So I'm gonna basically go into TikTok. No, what's TikTok? Not TikTok. I don't want. Anyway, so basically, I'm trying to make this formal enough for myself. No one else, just for myself. So I'm stating that the problem of unilateralism on unilateralism, unilateral, unilateralism, basically missing consensus. So you understand consensus in the framework of the system. I have to do a trust before that, but it goes to how you understand that the bipartisan tripolar consensus framework applies here via codex. So if you understand that it's like a system of coherence modeling, this kind of a system. Use some more work where quantum computers work. This is quantum radio system I'm using to model this. But think of this: you have an electron. Yeah. Now listen, Monday. You have two electrons, and they are superposition. The bypass, the bypass states. They have a true, or they have like a basically they're bipartite. That means they're tripartite, yeah, tripartite. So they can be you have to ensure the tripartite. We want to hold them to be bipartite. So we want them to be bipartite. So you don't want them to tripartite because they have that noise. So you're gonna have superposition interference and superposition interference. So basically, you got superposition entanglement, no interference, no interference. So basically, it goes to have you understand that this no interference is not a bad thing. It's basically the best thing you can have. Notice. So you can have a balance. So the bar part just means you have the state of the just like the tomography itself, but you're gonna have one being electron, one qubit, one two electrons in one qubit, be a quantum. A quantum. Think of them as radio. So the radio is more the what I got to give you. I'm trying to invert it for your radio. So you have a transmitter and a receiver, and I'm gonna have a relay system there. A transmitter. So the transmitter is no, listen, Monday. The transmitter is electronic. The receiver is magnetic. That's what you're going to understand. The transmitter is electronic. The receiver is magnetic. Simply, wherever the transmitter sends, the magnetic proton, the magnetic atom has to store it some kind of state. Bypass the store, so you have to store basically the spin. So if you store a spin of velocity and a position, if the magnetic system is measuring something from the other qubit, it's measuring what? It's measuring uh, basically the two radio system, two individual. It's measuring a spin, and that spin is basically has a position, has a tomography or topology. So you show as a position on the electron neutrino because the neutrino has mass. You're gonna stand with the same. So the electron neutrino has mass. You're gonna have a quantum spin of a half, what this quantum spin is, with a radio system. So you're gonna be getting information of radio. So you never have mass the electrons have mass on the electron side, but they measure spin. So they measure spin, but don't measure mass. So you're gonna have a system there. So we also need to understand that the radio system can jam radio system, which can jam system signals, but also you can have a relay system. So they can have a third relay observer that which just observes the state and see and replace commands like a third radio. So if I have a radio and I stick on a wall, and I wanted to unlock some kind of door, good or bad, it really can do it because your radio measures the signal. It can be relayed to the other system to replay the attack of the system. You get what I'm saying? No, no, I'm saying this is the reason why. Basically, I use a model to do my head, but I'm not doing weird analysis. I'm doing like competition with us with the model. It's no weird analysis. I'm telling you, it actually helps me the model. So I'm creating models in here. Models aren't perfect. That's why we call them weird. But I just want to acknowledge that for now, because I'm taking quantum radio, this, that. But if you want the simplest one of it, just think of qubits having two electron spins, one shell with two electrons spinning, and they have a velocity, and the electrons have a velocity and a position. But one electron, they both have the position. But, one electron is simply whatever. You have two sets of qubits, two pairs of qubits. But, when one opposite velocity, other opposite position and velocity. Basically, this give you two of stability. You also have the electron as how it gives the tomography or the topology of the system. So basically, that's where the topological term topology computing works on, which is the focus of this video. Yeah, I was thinking about monotony. Exactly. I was thinking about monotonic significance, not monotony, but I think it's a different term. Monotonically. I don't know what that term means. Monotonically increasing. I think they increase by the ratio of something else. But I think it relates to the problem of manifolds, but I don't really know how that can be defined in topology. But it basically relates to manifolds, and let me search the word manifold meaning. Manifold. It says here many or various, manifold, many or various, having different forms of elements. And you're gonna have monotonically increasing. Basically, I don't know what that means. Modular increasing function is a function that increases as the point over to x increases over the domain of its own domain. So the 2 points x and y domain if less than Then function f, in other words, this remains upwards trending, with no flat increase. The reason in between, monetary increase is again monetary decreasing, So this is like a function, monad function that grows in respect to an input. Yeah, I'm saying to you, it is all grind. Monotonicity, monotonic, either increasing or decreasing. But it's not monotonic, it's looking at stack exchange right now. It's like, give me three outputs. So I don't hate the output. I'm saying that if people have questions on trouble monotone increasing function. So I have some confusion. I have some confusion between monotones, increasing functions, and increasing functions and increasing functions. Yeah. So, for example, this guy wrote to AI is monotone increasing, and some function strictly is monotone strictly increasing. But if x is this function monotone increasing? Yes. Okay. So my God, basically, if you have a radio system that's quantum, you can have a universalism consensus model there. So I've stated this. You go this was the problem, yeah, but this is tomorrow confusion. I'm trying to have a magnetic tape. Magnetic tape, simply, basically, something that's magnetic. So it's remember that's magnetic. It's very good to have that kind of system of magnetic memory because magnetic memory just means that you're applying with your measuring stuff and you're actually storing stuff and you're actually processing stuff. So that's why I prefer to use it. But topology computer can hold hands with these stuff. Actually, the qubits can hold hands. Just I like to see, because they are extendable. They are qubits, so they like to hold hands. But that's what I'm saying. They like to work together. You know what I'm saying? So because it's a qubit, it's not a classical bit. You know what I'm saying? Thank you, thank you, thank you, mother. You're very beautiful.